So let's get to what the power actually is. Let's say we have something in the form a to the power n. That's going to be our base. That is our exponent. And then this entire thing is our power. This entire thing is just a generalization of what we know to be true. If we have something like 2 times 2 times 2 times 2, that we already know is equal to 16, but we can rewrite this entire thing, sort of an earned laziness, by saying it's equal to 2 to the power 4, and that's 16. So this is an example of what we know to be true. So let us revise the laws attached to this. Well, first off, remember, if we have the exact same base, however, if they have different exponents, we are allowed to add those exponents. Again, let's use 2 as a base and just have some examples. So let's say we have 2 to the power 3 multiplied by 2 to the power 2. That's just going to be 2 to the power 3 plus 2, which is equal to 2 to the power 5. And we can double check this. We know this to be equal to 32. Now, if multiplication leads to the addition of the exponents, then obviously it makes sense that division means we should subtract those exact same exponents. So that's going to be m minus n in this case. So let's just double check over here with our first example and reverse it. Let's say we have 32 divided by 4, we know to be 8, but our exponent law should give us the exact same thing. So that should be 2 to the power 5 divided by 2 to the power 2, which is just 2 to the power 5 minus 2, which is 2 to the power 3, which we know to be 8. So again, just from reverting from the generalization to a specific example, we can see these things to be exactly true. Then we have our power law. What if we have 2 to the power 2 to the power 2, or let's make it 3? Well, that's equal to 2 to the power 2 times 2 to the power 2 times 2 to the power 2. If we add them up, that's just 2 to the power 6. But we could have short-circuited that by multiplying, and that's what our power law says. If I have a to the power m, and I raise that entire power to another exponent n, I'm going to have a to the power m multiplied by n, as seen in this example over here, which we started with. Let's get another new screen. And then there's the case of, let's say we have a product and we raise that entire product to a power m. Well, in this case, because I am multiplying over here, I can say a to the power m multiplied by b to the power m. So that's taking care that I distribute the exponent and multiply it with the exponent in each of these factors that I have here, so a and b. And the exact same thing works when I have a quotient or a fraction. Again, just make sure that I apply the exponent to both the numerator and the denominator. And then finally, if we go back to primary school, we were always told that anything divided by itself is equal to 1. Well, let's just investigate this in terms of our exponent law. So this is our quotient of powers where we subtract. So that's just going to be 1 minus 1, which gives us a to the power 0. So if we put this together, we can say anything to the power 0 is equal to 1, which is equivalent to saying anything divided by itself is equal to 1. Well, how about 1 over a? Well, that can be rewritten as, remember we just established this, 1 can then be written as anything to the power 0. And then we have a, remember, if we don't see an exponent over there, there's a 1. Well, that can be rewritten as a to the power 0 minus 1, which is just a to the power negative 1. So putting that all together, we find that a to the power negative 1 is just equal to 1 over a. If we reverse that, 1 over a to the power negative 1 is then going to be equal to a. So another way to look at it, if I move the base from the denominator to the numerator, or vice versa, the sign of the exponent will change.